Okay, I just start at the point where we left yesterday because I was doing things in a hurry. So, let me redo that. You remember yesterday I discussed that any random process can be decomposed into two components. One is purely deterministic, that is purely predictable, and another is purely non-deterministic component. Deterministic is one where any sample can be predicted exactly from its all past samples. Typical examples were sinusoidal signals with random phase or random amplitude or both. Okay. But the purely non-deterministic is one where any sample cannot be predicted exactly from its entire past. So, the prediction here will have at least non-zero variance, that is positive variance. Okay. And then I said that in this course we will be discussing only the non-deterministic random processes. For non-deterministic random processes, spectra is continuous. For deterministic ones, I have said that they will consist of lines. Each line corresponds to one sinusoidal component. So, deterministic part actually can be shown as a summation of several sinusoidal components like that. So, we will be considering this purely non-deterministic component, that was Olds decomposition, and that further said that in this case the purely non-deterministic process xn can be written as though it is generated by driving a causal stable LTI system with impulse response Hn by a white sequence say Un. Okay. And then what we said is this, we use this for spectral estimation, parametric spectral estimation. We said as such the output per spectral density will then be what? Transfer function mod square times input variance. Input variance is just a constant because it is white. Okay. So, that means for this kind of processes, I mean if you have to do power spectrum estimation, I have to just identify that LTI system impulse response Hn, but again that has got infinite number of coefficients H0, H1, H2 dot 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 to H infinity, which I cannot do. So, what we do, we go for rational approximation, that is this same model we try to approximate by a rational model with zero initial conditions, of course, as I told you, unless you give zero initial conditions no system remains LTI. Okay. And that general, that is we are approximating in Z domain Hz by a rational form like B0 plus B1 Z inverse plus dot dot plus BQ Z inverse Q divided by 1 plus A1 Z inverse plus dot 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 plus AP Z inverse P. These are all there in your notes, I am not writing it here. In time domain it means a constant coefficient difference equation. This model is pole zero model, it has both poles and zeros, it is called also ARMA model. ARMA means autoregressive moving average. The left hand side where you have got xn, A1, xn minus 1, A2, xn minus 2, that is this is the autoregressive part. Auto means self, regression means this you are taking the past xn minus 1, xn minus 2, all these things. So, it is autoregressive part. Right hand side is called the moving average part. Right hand side consists of the nonlinear estimation problem because the coefficients B0, B1, B2 they are unknown, also the input white sample noise samples UN, UN minus 1 they are also unknown. So, product of two unknowns which is why it is a nonlinear part. And this is ARMA model. There is another model called MA model, rational model, where you forget the poles, only zeros, that kind of transfer function, then it is called MA, moving average model, where output xn is nothing but B0 UN plus B1 UN minus 1 plus dot 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 plus BQ UN minus Q. This is just a MA model, moving average model. Here two unknowns are multiplied, B's and U's. UNs, the samples are unknown, so are the B's. So, it is again a nonlinear estimation problem. We normally avoid them, and because the algorithms do not guarantee convergence or even estimates that come out, they are not very what to say, they are not best estimates, estimation errors are large and all that. The one which has really been a great success actually is the autoregressive modeling, AR model. In the AR model you have got all pole model. Okay, numerator coefficient can be B0 like this. Sorry, this is 1. Instead of A1 to AP, let me call them A1 prime to AP prime for some reason. This is driven by, this I did yesterday also, some process say UN or maybe U prime n is a white noise, zero mean white noise, white process. White process means every two, zero mean white process means what? Every two samples are uncorrelated and therefore they are orthogonal. Isn't it? And this is your xn, this is the model. In this case, in time domain, the equation is, of course, this model means you have to give zero initial condition. In time domain, this means xn because xz into 1, xn, a1 prime x n minus 1 plus dot 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 a p prime is b 0 into u prime n, but b 0 into u prime n you call it u n, because u prime n is white, b 0 into u prime n also is white, only the variance changes. Variance in any case, even here is unknown, I do not know the variance of u prime n. So, absorb b 0 into that and call it a white process, we will find out the variance of u n, that variance times transfer function square, that is z replaced by e to the power j omega, mod of that square into input variance, that will be output power spectral density, right. This is called the AR model, autoregressive model. This is a linear estimation problem, because on this side you have got the known data for x n, only unknown are the parameters. So, unknown into known, it is a linear problem. Okay. Then I said that suppose such a model is really true, it is a true model, that x n is indeed generated by a model like this. Our model order selection also is correct. Not only model, not only it is told that x n is a AR process. Such, I mean, any random process generated by an AR model will be called a AR process. So, it is not only told that x n is a AR process, also the order also given, that I chose order up to p. Suppose that order is given, okay, order is also correct. That means this is a true model. If this be the case, then I will say, I will show, as I did yesterday in a hurry, that these AR parameter coefficients, this filter parameter coefficients, they are nothing but what you would get if you do linear prediction of x n from its past p samples, that linear combiner coefficients combining x n minus 1, x n minus 2 up to x n minus p. Those coefficients are nothing but these coefficients. To see that, suppose I take the left hand side and project it orthogonally on the space, project means orthogonally project on w 1 comma p. So, this also you project on w 1 comma p. I am assuming this model to be causal and stable, that is an assumption. Okay, that is an assumption I am making, that this model is causal and stable. So, its impulse response, if it is h n, that means x n is nothing but convolution between h n and u prime n, or rather h n and u n you can say in this model, or h n, okay. You can drop this b 0, you can make this now equal to 1 and you can call it, you can now call it u n, okay, and h n. So, x n is h n convolved with u n, so as I did. So, since it is causal and stable, you have to start at h 0 into u n plus h 1 u n minus 1 plus dot dot dot. But u n is an orthogonal sequence, u n minus 1, u n minus 2, they are all uncorrelated, white, so uncorrelated. So, that means if you say x n minus 1, my claim is this is orthogonal to u n. Why? Because x n minus 1 is dependent on what? U n minus 1, u n minus 2, u n minus 3, all that. So, that is orthogonal to u n, because u n is orthogonal to all the past samples, u n minus 1, u n minus 2, u n minus 3, because u n is a white process. Similarly, in fact, I should say now x n minus k is orthogonal to u n, where k can be 1, 2, dot dot dot. So, if we project u n on the space spanned by on the w 1 comma p, what is w 1 comma p? Space spanned by x n minus 1 up to x n minus p. Now, u n is orthogonal to all of them, that means u n is orthogonal to this space. So, that means projection error is 0 and u n itself is the error, sorry, projection is 0 and u n itself is the projection error. So, projection here is 0, you understand, na? It is perpendicular to that space, mathematically also you can see. If you consider an external vector, okay, say x in a vector space, V is a vector space, W is a subspace, okay, small v is a vector lying outside W but inside V, you know V can be orthogonally projected on W. So, V is nothing but a summation of projection and the error. Okay. If V itself is orthogonal and then there is a Pythagoras theorem easily seen, norm square of projection plus norm square of the error equal to norm square of V. If V itself is orthogonal on W, then that projection will be 0. You can easily apply that Pythagorean logic here. So, and projection is 0. That means this side if I project, I get 0. 0 means 0 random variable, mind you, and this side I get P1 comma Pxn, because I am projecting it on W1P, plus projection is a linear operator. So, projection of the summation is nothing but individual projection summed. So, projection of this guy, say A1 prime, because of linearity it goes outside, it is a constant, times projection of xn minus 1 onto W1 comma P, which is xn minus 1 itself. That will give the minimum possible error between the two, which is the 0 here. So, you will get this, and same for others. Isn't it? But we know that P1 Pxn is what? Plus, that is, if you write this way, A P1, you know our notation, projection is nothing but, you remember I said that it is summation and I put a minus sign with the coefficients, linear combination of xn minus 1 to xn minus p, there was a negative sign with the coefficients I used. So, if you bring that to the left hand side, they become plus, isn't it? Now, if you just take these two, obviously, if I say by comparing A1 prime is this, AP prime is this, but mathematically if you subtract from this one from this also gets subtracted, and A1 prime minus this AP1 into xn minus 1 plus A2 prime minus AP2 xn minus 2 plus dot 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 AP prime minus APP into xn minus p equal to 0, those are linearly independent samples. So, obviously, its coefficient is 0, A1 prime equal to AP1, A2 prime equal to. So, that way you understand that AK prime becomes equal to APK, K can be 1, 2 up to P. Okay. So, these AR model coefficients are nothing but the linear predictor coefficients. These coefficients are called linear predictor coefficients. Okay. Now, I said that model must be causal and stable, and that fact I have used here. That fact I have used here, under that only, using that only I got this relation. There is nothing but linear predictor coefficient. But how can I justify that this is indeed causal and stable? That I proved yesterday, that if you do linear prediction, then the linear predictor polynomial is always causal and stable for any order. I proved that yesterday. You remember using P.P. Vaidyanathan's proof? Whichever is the order, Pth order, P plus 1th order, P plus 2th order, any of those polynomials are minimum phase polynomial. Roots lie within unit circle, isn't it? So, this part is a linear predictor polynomial, but this has now gone to the denominator. So, that means roots here which are poles, they are lying within unit circle. That is guaranteed from linear prediction theory, which I proved yesterday. That means this model is such that it has all poles lying within unit circle in Z plane, which means it is causal and stable. So, to identify or to do AR modeling or to identify equivalent saying, to identify these parameters, what you have to do is simply to take xn and generate those coefficients, these coefficients. If it is a pth order model, generate these coefficients AP1, AP2, APP. Those will be these model coefficients. How to generate the coefficients? We have seen this approach already by using lattice. That lattice algorithm. In the lattice algorithm, we are updating sigma p f square, sigma p b square, delta p's and all those. And there again API and BPJ, they also are updated. We started with the given statistics of xn, using that statistics. You may not be given x, you may be given a data record of xn. So, by sample average, you find out its autocorrelation values, estimates. Give that to your lattice algorithm. Lattice means not the lattice filtered, because I am not interested in the online operation of the lattice filter. I am only interested in the lattice algorithm means recursive computation of sigma p square, delta p's and those AP and BP coefficients. Go up to the order p, because it is a model order p, and you get those coefficients. Those will be nothing but the corresponding AR model coefficients, and that will guarantee causality and stability, because that amounts to a filter with roots within unit circle. That is what we proved last time. Okay. Mind all these things we are doing. Okay. Now, I mean, this is my approach, that is do linear prediction, use the orthogonal projection of treatment using vector space concepts, get all lattice, okay, forward prediction error, backward prediction, everything, and link AR modeling with this by this theory, and therefore you obtain the AR parameters from just those coefficients. But in book also there is another approach where vector, the approach is for those who are not familiar with vector space theory. They find out these coefficients by developing an equation called Euler-Euler equation, solved by, some of you know, Levinson-Darwin algorithm. Okay, I will just narrate that because otherwise you may get confused in future seeing some algorithm and you may wonder as to what is this. Okay, this is nothing but an equivalent way of obtaining those sigma p square, delta p's, and those AP and BP parameters. Now, to do that, you see one thing. If you know there is no AR model, even when there is no AR model, I can have an equation like this where UN is simply EPFN, and these are the predictor coefficients. There is a more general way of writing. In the case of AR model, what is the difference in the case of AR model? Can you tell me? This is always true. Suppose I am doing pth order linear prediction, then xn, and if these are the predictor coefficients, then this is always equal to EPFN. EPFN is orthogonal to xn minus 1 to xn minus p. In the case of, okay, but now suppose it is not only linear prediction, I have also the AR model. So, for the case of AR model, I also have the same equation. What is the difference between just linear prediction and AR model? In the case of linear prediction, UN is EPFN, it is orthogonal only to xn minus 1 to xn minus p, not to xn minus p minus 1, not to xn minus p minus 2. But when it is AR model, this thing which is not only EPFN, additionally it is also the input that is orthogonal to all the past of x because of this relation. Please see the thing, this equation is always true. This equation is always true. Some noise process. This is always true. This is orthogonal to xn minus 1 to xn minus p. Okay, but if I only am solving linear prediction problem and there is no guarantee that xn itself is a AR process, that it also is satisfied that AR model, then I cannot say EPFN is orthogonal to xn minus p minus 1, xn minus p minus 2, xn minus p minus 3. That I cannot say. But if additionally it is said that XR also is an AR process, that we have seen pth order AR model, pth order AR process, then you have seen this is nothing but, this turns out to be what? These are the predictor coefficients, also AR model coefficients, and therefore this is nothing but, this prediction error is nothing but an input white process. But that is orthogonal to, because of that causality of that system and all that, is orthogonal to not only xn minus 1 to xn minus p, orthogonal to all the past. So, linear prediction problem, this is actually to start with, it is a linear prediction problem. EPFN is always orthogonal to xn minus 1 to xn minus p. Additionally, if it is also a AR model, if xn is a pth order AR process, EPFN is orthogonal not only up to xn minus p, but to even all past samples of x, because in that case this turns out to be the AR model input white process. You can see one thing, one more difference. Suppose you are solving a linear prediction problem, there is no guarantee that EPFN and EP say Fn minus 1, they are orthogonal, because what is EPFN? EPFN is xn you are projecting on what? W1 comma p, and this error. And what is EPFN minus 1? Somewhere in this space is your xn minus 1, that is projected on another subspace that consists of xn minus 2 up to xn minus p plus one more element. So, there is no guarantee that these two projection errors will be mutually orthogonal. Are you getting me? So, it is not necessarily a white sequence, that EPFN, EPFN minus 1, EPFN minus 2, they are white, not necessarily. In the general linear prediction case, they are not. But if additionally an AR model is given, then it is given that Xn also is a pth order AR model, then we have this additional thing about this EPFN are these coefficients. Coefficients are the AR model coefficients. EPFN is not only linear prediction error, it is also the AR model input, and therefore is a white sequence. It is orthogonal to not only Xn minus 1 to Xn minus p as is valid in the linear prediction case, but it is orthogonal to all past X. These are additional things that come up in the AR model case. Are you getting me or not? What all is valid here? This is always true for linear prediction. This is orthogonal to space span by Xn minus 1 to Xn minus p. EPFN minus n is orthogonal to space span by Xn minus 2 up to Xn minus p minus 1. There is no guarantee that these two will be mutually orthogonal, because the two spaces are different in general. Okay. But I said that I have just proved that if Xn is given to be a pth order AR process, there is indeed a pth order AR model driven by a white input, then we have proved that AR parameters are these predictor parameters. This part is the predictor, negative of this is the predictor, original minus the predictor is the error, and this error is nothing but input white process. So, this EPFN will be a white sequence. Further, this will be orthogonal not only to Xn minus 1 to Xn minus p, as is valid only in linear prediction case, it will be orthogonal to even past value, further past values of Xn, Xn minus p minus 1, Xn minus p minus 2, all up to x minus infinity. Okay. So, to remain on the general case, we do not consider AR model now, we are just consider the linear prediction problem. In the lattice also we are solving linear prediction problem, we did not assume any AR model. Here also I am not assuming any AR model. I have only linked it up with AR modeling, so you understand what is the relation between AR model and this. That indeed AR model is valid by solving linear prediction problem, you can get the AR model parameters, and EPFN, this prediction error then satisfies some property, it is a white sequence in that case, all those things come up. But now I consider this linear predictor problem, because if I solve this, I mean if I can get these coefficients either by lattice method or by some new method which I said just now, Euler-Occam equation and Levinson-Durbin-Recursion, these coefficients if I get, it is enough, because if there is an additional AR model assumption made or condition given, these coefficients itself, these coefficients themselves will be my AR model coefficients that I have proved. So, it is better that we start, we just look for linear prediction problem only, we do not assume any AR model thing, we find out a technique to obtain these coefficients. We already know how to obtain the coefficients via lattice method. The other method which is given in books, and especially for those who are not initiated to vector space, that is why I will just consider, but again I will not take it to the end, I will only start give the basic equation, basic philosophy, that is all. Okay. Yeah.
Xn minus 1 that we have drawn here, so that will be projected on a new subspace.
Xn minus 2 up to Xn minus p minus 1. So, there is a new subspace.
New subspace. So W2, that will be named as W2, comma p.
You can say so, yes. Yes. And there is no guarantee that these two errors are mutually orthogonal. As such, in general, there is no guarantee. Find out when they will be orthogonal. Just what should be the property of Xn so that those will be orthogonal. Just for your fun or practice, just take it up back home. When this prediction error sequence also will be orthogonal. Just do it. I can see it, but you try do it. That will have some geometric insight. It is not difficult also. Anyway, so that alternate method I just touch upon here, that is called Euler-Occam, or also pronounced as Euler-Occam equations method. Equations, Levinson, Durbin, Recursion. We have done this Levinson-Durbin already without knowing that we are solving a set of equations. Remember, I obtained a p plus 1 comma I, all those coefficients from a p comma I and b p comma j, that is Levinson-Durbin recursion actually. But here people in textbooks, I mean on spectral expansion especially, they approach this entire thing from just some algebra point of view. Consider this equation. Now, this equation, my purpose is to find out these coefficients. Now, I know EPFN is orthogonal to xn minus 1 to xn minus p. Okay. So, suppose, I mean I write like this, and for the time being, in order to make life simple, let us assume everything real, no complex data. Okay. Then again everywhere I have to be cautious and all, just complex. So, suppose I write like this. I am doing this way because I want to save time. This vector I will call x n transpose, and this is I will call a p vector. This is equal to E P F n, right? Suppose so this equation is x transpose n A p is E P F n, right? I multiply this left hand side by x, a vector. How to name that vector? Okay, I multiply this by, say, I am doing many things in one step, because I really want to be precise here. Multiply this by this, A p. So, this is your, okay. Now, I take expectation. So, obviously, you will work on this. A p is not random. A p is not random, isn't it? Data is random, A p is not random because of stationarity. That is our assumption. Remember, why A p is not random or A p is constant and all that, because of stationary assumption that I made. Never forget that. That comes for fundamental optimal filtering thing. Okay. This E working on this. This will be R, and again R independent of n because of stationarity. R what size? P plus 1 into P plus 1. After all, this vector has got how many terms? P plus 1 terms. Isn't it? So, R P plus 1 into P plus 1 into A p, and this vector here you see is a cross correlation thing. X n has got all those components. Now, if you leave aside the topmost component in x n, take the second and downward, all the correlation terms will be 0, because E P F n is orthogonal to x n minus 1 to x n minus p. Okay. So, you will have things like this, a 0 vector. I am not writing the size, you can make it understand what the size will be, and first term will be what? X n into A P F n, and then expected value, that is inner product between x n and E P F n, and that I can write as inner product between E P F n and E P F n. You remember, I can shift that projection operator and all that. I am not doing it, please. Okay. So, this is sigma p f square, say f square. I do not know here, since I am not doing lattice method, I do not know whether sigma p f and sigma p b are same. So, I am writing this. This is the form. Okay. This is called Euler equation. This equation, mind you, this equation is a bit, I mean, it is not in the usual form, because this is a matrix times A p is an unknown quantity first. I do not know input, I do not know this prediction error, this quantity is to be known, isn't it? You remember in lattice also we did not know this, we are updating it. We do not know this, so this is unknown, and then zeros and A p. So, this is not a usual A x equal to b kind of equation, it is just, but actually it is, because what is happening is the form of the equation. If you see, how many are familiar with Levinson-Turbine here? Nobody. In our department, in digital communication course, people to teach. Anyway, these are matrix or, since only one process, I am not giving the subscript or XX and all that, because that will consume too much of space. R means I am referring to the process X n only. I am dropping the subscript XX everywhere. Okay. R0, R1 dot 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 Rp, then again R1 real. So, I am not putting R minus 1 or R1 star and all that. You understand now? R1, R minus 1 they are same. So, it is R minus 1 which is R1. I told you about Toeplitz matrices in the context of optimal filter. This is the correlation Toeplitz matrix. This Toeplitz is beautifully exploited here in this Levinson-Durbin business. Into 1 AP1 dot 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 APP equal to an unknown quantity sigma p f square 0 vector. What is the meaning of this equation? You see the way to look at this equation is this. First, forget about the first row. Forget the first row. Forget about this row times this column. That will give rise to one equation. This row times this column equal to sigma p f square. Unfortunately, right hand side is an unknown quantity there. Don't look into that equation for the time being. Consider from second row onwards. What is it? 1 times, that is if you have this part only, and forget about this element. These are right hand side, you have got zeros. And I told you how to do matrix into vector multiplication. You remember 1 times this column plus this submatrix times this vector is equal to all 0. So, take this column to the right hand side. So, this submatrix times this unknown vector equal to a column on the right hand side. So, you solve that. I am assuming all these matrices are invertible, that is positive definite. They are correlation matrices, in general non negative definite, but I am assuming positive definite. Okay, so they are all invertible and all solvable. So, once you find the coefficients, put them back here, then carry out this row times column, you get the unknown quantity on the right hand side. This is the way to go about. Okay. Now, one thing you can see, this R matrix is such, R matrix R can be written like this. I can take out this part. So, this submatrix is nothing but autocorrelation matrix of one order less. Instead of R0 to Rp minus 1. Same thing is propagating. Na? Okay. So, this is, we write like this. Some elements here, I am not writing them, some elements here and here, but essential thing is, it is also instead of p plus 1 to p plus 1, let me call this p plus 1, because too much of space was consumed here, p plus 1 into p plus 1. When I say p plus 1, where R is capital, so it is a matrix, p plus 1 means p plus 1 into p plus 1. So, this is p. At the same time, I can have a partition, forget about these dots, you can also partition like this. Same thing we will get Rp and some elements here, some elements here, some elements here. This comes due to the Toeplitz nature of the matrix. Same submatrix is sliding down. Same submatrix has come over here. On top of it, there is symmetric also. Though symmetry is not really needed very much here. Non-symmetric case also I can apply Levinson-Durbin recursion. In fact, it is done in AR model, ARMA, in the AR estimation part of ARMA modeling problem. That this matrix is not symmetric matrix, but Toeplitz, and that is enough for Levinson-Durbin to work. The way they go about there is this, that okay, you are solving an equation like this. Why not also solve another equation, which is actually the backward prediction equation. What is the backward prediction equation? That is, if I have sorry, This I can write as x tilde n transpose, I will tell you what is tilde n, times BP vector as EPBN. My definition is, given any vector x as say x1, x2 dot 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 say xn, x tilde means you just reverse the order. X tilde means just xn, xn minus 1 dot 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 x1. Okay. First element becomes last, last becomes first, that way. So you understand? We know what is xn. Xn vector starts at xn up to xn minus p. I have made it tildification. Okay. So it's xn minus p to xn, and then row of that BP vector. BP vector is, my definition is BP vector or maybe let us not do tildification here. I can observe that here only. B p comma p, okay, tildification I will do later. 1. This is my BP vector. Okay. And then I take this xn, I multiply. So here also I multiply xn, okay, and take expected value. Here also you take expected value. So xn into x transpose, there is r, BP, r is rp plus 1, size is p plus 1 again, into BP. Now this vector EPBN is what? Xn minus p projected on all the p future terms. I mean the space spanned by the future terms xn minus 1 up to xn minus p plus 1 and the error. So that error is orthogonal to whom? This error is orthogonal to top component, next component, except for the last one. So you will have 0 on top and last value is xn minus p, that times EPBN and expected value inner product between xn minus p and EPBN, which again by shifting that projection operator and all, I will not do it here. You know that turns out to be inner product of EPBN with itself. So this is sigma p b square. So this Levinson-Durbin says that you solve, instead of solving one equation like this, solve both the equations simultaneously and recursively for various orders. That is what we do in lattice. What we do in lattice, this is just that algebraic version. That is, if you take out that vector space street plane, the inner vector space meaning of all that, just look at it from equation solving point of view, then you have that. You simultaneously solve a forward and backward prediction error problem, order recursively. If I assume, I will assume that say solution for p minus 1th order is known for this equation also, this equation also. Then how to solve this and this equation? Okay. So suppose p minus 1th order, but the matrix would have been Rp, that is known to us. Okay. How to solve for pth order? So the way they go about, and again, I will just give that indication and stop, because we will basically get the same equation. I am doing it so that at least I am doing the formality of Levinson-Durbin, with the purpose that when you see books or come across Levinson-Durbin, you don't get confused thinking that it is something else and all that. You see the formulation of this. So now I say that there are two equations. One is, you can now write Rp plus 1 into Ap is equal to this form, this equation, another is this equation, these two equations. And I have got that, this decomposition of R. Okay. Now start with any of them. Suppose you are solving this. Remember, you have got all zeros here, only one non-zero component and all zeros. Okay. Then people say that suppose that unknown solution Ap, can I write it like this, Ap minus 1 I am just constructing a solution and see, I will give you the logic for this kind of, and some coefficient k p minus 1 into b p minus 1. Right? This is an unknown to be found out. What is the logic for this kind of construction? If I put that here, this in this first equation, r p plus 1 into a p, AP is, this is the equation to be solved, isn't it? 0 vector. If you put that here, if you replace AP by this, okay, by the way, just a minute, I was making one mistake, it's not, let me do it on a separate page. This is a dimensionality problem. AP has got how many coefficients? 1 and p coefficients. AP minus 1, how many coefficients? On top 1 and p minus 1 coefficients. So, the two vectors are not same, is it? I have to put a 0 to make them same. I mean, one is of length 1 higher than the other. Our basic equations I am writing into AP is sigma p f square by 0. This is one equation, another one was into BP. Okay. AP was 1, then A 1, then AP comma 1 dot 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 AP comma P. That suppose I am saying this is to be found out. I know its value for the P minus 1th order, AP minus 1. Suppose I know that. I am saying that suppose I construct a solution like this, and this is a equation, it will have only one solution because this is an invertible matrix. Ax equal to B, A invertible means solution is unique, A inverse B, isn't it? So, I have constructed a solution. If it qualifies to be a solution, that is the only solution, because this equation has a unique solution. So, I am just trying to construct a solution. You will see immediately that this way you can construct a solution. Kp, say I am calling it even Kpf, so times 0 Bp minus 1. Suppose I put like this, and I want to put it on the left hand side. Right hand side, this is unknown. Essential thing is, will I get a block of zeros if I put it here? So, first Rp plus 1 into this. What was the breakup of Rp plus 1? I did it in the previous page. Rp and some terms, and also Rp and some terms, right? You remember this, no? This one. Either this top square matrix is submatrix is Rp and then some one row, one column, or first row, first column, then Rp, right? Now, if I substitute this for AP here, Rp plus 1 will work on this for the first. That time suppose I use this form, that means Rp into AP minus 1 plus these elements will multiply the 0. This row times this, the last element is forgotten because of the 0. Second row times this, last element again multiplied by 0. So, last element has got no impact, it is only Rp times AP minus 1, that is the previous Wheeler-Ocker equation for P minus 1th order. Okay. That is, here you have got Rp AP minus 1 and this row times this, there will be some element. You see, I am done with this part times this I am done with. Last row times this will be some quantity, but that quantity I can work out because I know these terms, I know these correlation values, I know the AP minus 1. This is what manually you have to compute. If this is the thing which you do in the delta P computation. Remember, in the delta P computation I told there is no recursion possible, you have to carry out the sum. This is what is equivalent to that.
AP minus 1 transpose.
Yeah, those things will come up. So, here actually if you really put those terms Rp, what are the terms here? R, P, R0 dot dot dot, those terms times AP minus 1. But my purpose is not to get the exact figures and all, I am just giving the philosophy used in because of solving this, but I have already solved it by lattice method. I am only telling you what they do. So, you get a known quantity here, we call it delta PF. Fine. This is a known quantity. What is the known quantity? Inner product of this row times this row times this column, but this is known. And next one is KPF times RP plus 1. This time I will use this breakup, this into this vector. Okay. So, first row times this will be something, you can call it beta PF, okay, some known quantity. But after that what you have, first element times 0 gone, then RP, all the first elements they get multiplied by zeros. So, you essentially are left with RP times BP minus 1, and these are all previous order, P minus 1th order that Weyl-Oecker equation. So, this was giving rise to sigma P minus 1 F square, then zeros followed by delta PF, okay, and KPF beta PF. This is the previous equation of this kind, only thing is instead of P plus 1 it becomes P, it is P minus 1. So, it is 0 and sigma P minus 1 B square. I want this to be of this form, that is a positive quantity. I want this positive unknown quantity and then zeros. Here zeros are coming. See, this guy plus KPF times this is known to be from the previous order solution, this is known to be from the previous order solution. If I know KPF, suppose I know KPF, in that case this plus KPF into this will be this unknown quantity that is obtained. Then there is a series of zeros here, there is a series of zeros, 0 plus KPF times 0, they will restore those zeros required. Only the last row, that also has to be rendered into 0. So, that means this plus KPF times this must be equal to 0, but this is a known quantity, so that gives you KPF. So, you solve for KPF, KPF is minus delta PF by say beta by sigma P minus 1 B square. That KPF you put back here, you get this term. A similar approach exists for this case, backward prediction case. I am not doing that. Similarly, in the backward prediction case also a similar approach exists. Okay. That is there. I am just writing the solution. There, to this BP you find out, this BP you write there as this only 0 dot 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 B P minus 1 and say K P B zero. That is, this vectors remain same. Earlier this plus KPF times this, and next time this plus KPB times this. I use those factor, this decomposition of this matrix, and use the same philosophy. Evaluate KPB. That there you can try to prove that this delta PF square, delta BB square, they turn out to be same because of symmetric Toeplitz nature of the R matrix and all that. Whatever is the in the R matrix, first row terms and last row terms, they are same. Okay, because of Toeplitz nature and symmetric nature, all those. That is why those will be same. Sigma PF square, sigma P. This you can try to prove there directly, which we did by using vector space treatment in the lattice. So this is another treatment used. This is just simply equation solving treatment, but here you don't get to know what is happening inside. The other reason why I prefer that vector space treatment is that I will now go to first adaptive version of that lattice, but after that I will move to what is called recursive least squares, not LMS type, another class where that vector space formulation will be the key. Absolutely similar treatment. That is why I think the best formulation for this adaptive filters and spectral this linear prediction, is that vector space treatment. Okay. So, actually I thought that today's class will be gradient adaptive lattice, which I have to continue tomorrow, Gradient so far the lattice filter that you have considered, that is given by some constant parameters Kp, where mod Kp is less than 1 and all that, and Kp is given by delta p by sigma p square and all that. If you know the input correlation, you know those values, construct the lattice, fine. But suppose input statistics is changing from time to time, so and you do not really know those statistics. So that means like a adaptive filter, here also you have to make them adaptive. Okay, suppose input statistics is changing from time to time and you also do not know. So you have to learn from the data and adapt, going into an adaptive mechanism by which those coefficients, reflection coefficients, okay, you have to have an iteration on that LMS like manner, so that they will finally converge on their actual optimal values. Okay. So that lattice is called adaptive lattice, or called gradient adaptive lattice. Unfortunately, there is no time to this, so I will concentrate tomorrow. Thank you.